So let's look at another important quality of convolution. So we're looking at convolution with a shifted impulse. So if we had a function f of t, whenever we found the Fourier transform, it gave us the function f of I omega. If we had a delayed impulse, delta t minus t naught, it's equivalent to e to minus I omega t naught. So it's equivalent to adding a linear phase on in the frequency domain. Now we've seen that whenever we went over the delta function a few videos ago. So if you're unsure about that, you can always go back and have a look. Now we know that convolution in the time domain is equivalent to multiplication in the frequency domain. Again, we proved that in a previous video. So if I was to convolve these two functions, that is f of t convolved with delta t minus t naught, it would be equivalent to multiplying these two functions in the frequency domain. So that would give us e to the minus I omega t naught f of I omega. Now again, we've seen a couple of videos ago that if we were to delay a function, so the function f of t gets delayed by t naught, well that would be equivalent to taking the Fourier transform of the function and adding a linear phase onto it, so it would be e to minus I omega t naught f of I omega. So we can see that this f of t minus t naught when the Fourier transform gives us this here. But this here is exactly the same as the line above. So therefore we can say that this thing here, f of t minus t naught, is the same as what we have above. So just convince yourself of that. We're just going round about this square. This here equals that, but this is equal to that, therefore this must be equivalent to this here. So therefore we can say that the f of t minus t naught is equal to the f of t convolved with delta t minus t naught. So in words, what we can say is, if we were to time shift a function, it is equivalent to convolving the function with a time shifted impulse. So just read through that again. If we time shift a function, it's equivalent to convolving the function with a time shifted impulse. Now there's a lot involved in that there, so read over it again and convince yourself of just a simple little bit of the logic that I've worked through there. But it's much easier to understand it graphically, so let's go ahead and we'll look at a graphical example. So let's say we've got the sinc function in the time domain. Whenever we Fourier transform it, we get this square function in the frequency domain. Now let's imagine we have an impulse function, but it's delayed by a value of t naught, so it's the impulse function sitting at t naught. Well, we know that this is equivalent to just adding a linear phase, so this is the linear phase here. So if we were to convolve these two functions in the time domain, it's equivalent to taking this function here and just shifting it on to the t naught, so it just recenters it at t naught. So when we convolve these two functions in the time domain, it's equivalent to multiplying these two functions in the frequency domain. So in effect, all that's going to happen is that this function here, the square function, is going to be multiplied by the function which shifts the phasors round by a certain value, a certain angle, which is given by the delay here, t naught. So in the end, we end up with a function here, which is a complex function, which is just the square function there with the phasors having rotated round. So that really shown is what we've been looking at here in terms of a convolution with a shifted impulse. So let's have another little look at this and another example live in MATLAB. So we're going to use this function again, f1, in order to look at the Fourier transform of the function here, which is a little square function which has been delayed slightly, so it's no longer sitting at t minus 2t plus 2. There's a slight deviation there, so it means that we've shifted that function along in the time domain. So again, this little function is available in the resources section, so you can go and copy and paste it in. So let's have a wee look and see what the output looks like. So this is the function here. Now you can't quite see it here because it's quite small, but it's not sitting actually centred on 0, it's shifted slightly along in the t-axis. So it means that if I were to look at the Fourier transform, now the real section of this would give us something that would be similar to the sinc function that we'd seen if the function here had been sitting centred on 0, that is, it would have been a purely real function. But now that it's shifted along, what's really happened is all these lobes are starting to shift in the frequency domain. So you can see this, all these lobes starting to move. There, you can see it better there. So all the lobes were sitting straight up, now they've all started to shift in that complex frequency domain. So you can see that here. So now let's finish off by noting that we can do the same thing in the frequency domain. We can take a function f of I omega in the frequency domain and we can delay it by a certain value at omega naught. Well, that's equivalent to taking the impulse function in the frequency domain and delaying it by omega naught and convolving it with a function f of I omega. So it's the frequency domain equivalent of this same effect we see in the time domain. So that's all there is for this video. I'll get you in the next video. Goodbye.